Hey everyone, in this video I'm going to show you how I made a program to find the square root of a number n using 8085 for my project in my course PHN 314. So with that, let's get started. During my research for this project, I came across a lot of variations to find to model this equation y square equals to n, and some of these are given in this slide. As you can see, in the first three approximations we are using recursion relations, and the second one is Newton's method to find the roots of this equation. So finding the square root of n is basically finding the root of this equation. This can be simplified using a normal algebraic manipulation, and you can see this equation will turn out to be this equal to this, and this last equation is just y is equals to n by y. The y has I've just divided both the equations by y. So these can be used to find the square root, but our aim whenever we design a program, when we have limited resources, is to minimize the number of divisions and multiplications, because they are the most time consuming operations, and the first one uses one division, so this is already inefficient. The second one is already out of the question, because this function will uh, have this equation y square minus n, so you would have to calculate y square 2 and then divide by some number. Then the third equation also uses a division, so that's also out of the question. We can use these equations to find the square root, but it will be inefficient. So I continued my research, and I found these three methods too. So these two expressions, the first one and the last one, you can all remember from your high school. These are the summation formulas for n and 2n minus 1. The summation formula of n contains n square and n, so we can find n by using this, but it is harder to implement when we compare it to this formula. So I went ahead with this formula, the summation of 2n minus 1, which should be equal to n square. We can also use binary search, but the binary search would also include multiplication of the term by itself. I mean, finding the value of n square for each element in the sample space, so that would be inefficient too. In this formula, I will show you that why this is the most efficient we can use way to find the square root, and let's move on to the next slide. So now this formula is going to be implemented as a loop. The first, you can see that for a perfect square, this summation should be equal to n square. But what if it's not a perfect square? Then this value should be close as possible to n square as it can be. So for the first iteration, you just assume that the value of n is 1, and then subtract to n square minus 1 and check if it's greater than 0 or not. If it's greater than 0, then there won't be any carry, so you can check that by jc command. And when you move on to the next iteration, you want to subtract the sum of the series of odd numbers from n square. So you also have to replace the value of n square by n square minus 1. So the next term 3, when it gets subtracted from n square minus 1, it gives us n square minus 1 minus 3. The value of the series is also subtracted that way. So we just have to first do this subtraction, then replace n square by this, then this subtraction, then we carry on, and finally we reach a k which gives us the value n square minus 2k, the summation of 2k minus 1, which when it goes beyond 0 or it becomes negative, we check for carry and then stop the iteration. Then that value of k would be greater than n square, the integer greater than n square, which and greater than n, which gives us value greater than n square. So we subtract 1 from that k to get the least integer, which least uh, number which when squared gives us the closest number to n square. So now uh, when I was finding and searching for various ways to do this, I didn't come upon any algorithm to find decimal uh, to find square roots of decimal values, correct up to decimal values. So I thought that it would be great if I could implement this, and I did this by uh, a little trick that you can see. If we have to find the approximation correct up to first decimal place, we can, and we cannot implement that in 8085 directly. So we can do that. We can do this instead, that you can multiply n square by 100 and then find the under root of that number. So that would be 10n, and the least significant digit will signify the decimal place, the number after decimal. So as you can see in this example, n square equals to 10, and you have to find the approximation close up to first decimal place. So you multiply this by 100, n square into 100, and then the square root is 10 into n, and all the square root, the correct square root is 3.162, but we won't be getting 0.162 if we just enter 10. So we enter 1000 instead of 10 and get 31. So we know that the last digit signifies the value after decimal, so we just assume that decimal to be 3 and 1. So now this is the flow of the program, and first you enter the value 100 into n if you want the approximation to be correct up to first decimal place. Then you store that in HL pair, and then you store BC in 01 in BC and 01 in DE. The value in BC acts as a counter for the uh, number, the kth iteration. So the value in BC shows which iteration the program is in right now, and the value in DE is the value of 2k minus 1, which has to be subtracted again and again from the n square. So after that you subtract first HL, first DE from HL. So it utilizes 16 bits subtraction, and then it gives us a value which we check for carry to ultimately check if it's a negative number or not. If it is not a negative number, then you increase d by 2 to get the next term in the odd series, and then you increase the number of iteration by 1 to uh, move on to the next iteration, and then you again subtract DE from HL, and you do this until you get carry equals to 1, which will signify that the resultant is negative. So if the resultant is negative, then you subtract the then you want the kth minus 1 term, because that is the smallest integer less than the actual square root. Then you store the result and stop the program. So let's move on to the code now. This is the code for the program that I wrote. As you can see, I directly store the hex representation of the number 100 and into HL pair because of convenience. Then you store P and 1 in B and 1 in D. Then you move on to the subtraction part of the code. This block subtracts two 16-bit numbers. You do that by first moving the value of L. If you want to subtract DE from AL, from HL, then you move the value of L to A and subtract E from A, then you move A back to L. Then you do that again with H and D, but instead this time you subtract with borrow. So now if still there is a carry left, then that means that DE is greater than HL and the program should stop. So with that we subtract 1 from B to get the kth minus 1 term. Then you move C to A to store the final result. If the carry is not 1, then you increase the D 2 times and increase B 1 time as explained in the flowchart, and that is it for the code. Now let's test some values. So let's assume we have to find the under root of 10 for correct up to 1 decimal place. So you do this, you get the hexadecimal representation, and you wait a second, enter that into the HL pair. There should be a 1. Okay, so now let's run this program. The answer is 31, which is stored in the 0th memory location as given as STA000H. So the answer stored is 31, and the square root of 10 is 3.1. So that is what we wanted to do initially, and let's check with another example. Here is 20. We want to find the square root of 20, and the hexadecimal representation is 7D0. Now let's run it again. We get 4, and the actual square root is 4.4 something. Now let's try with 550. So now the hexadecimal representation is 1388. Now let's run it again, and that gives us 70, which is close to 7.07, which is the actual square root. The square of 7 is 49, so it's going to be close to 7. Now let's run it for 81. It should give us 90, which should be read as 9.0 because the LS digit signifies the number after decimal. So the representation is 1FA4. Now let's run the program again, and that gives us 90. So this, as we can see, this program is doing what we wanted it to do, and with that, let's move on to the presentation. Now, as we saw, the value of n square is, we tried some of these values and we got these results 31, 44 and 70 and 90, and the actual, as you can compare these with the actual, and they are correct to first decimal places. So with that, I conclude my video presentation, and thank you all for watching. Have a good day.